Today's presentation, I'm going to be talking about the Rotary encoder and potentiometer. The rotary encoder and potentiometers are part of our layer 3 architecture. I've put in a marker in the items that we need for developing our program associated with rotary encoder. And that also gives you an idea why rotary encoders go in layer 3. So the agenda for today. So I'm going to talk about encoder potentiometer. Then I'm going to show the differences with one and the other. And at that point, I'm just going to talk. After that, I'm just going to talk about the encoder. And the reason is because during my presentation on analog to digital converters, I already developed the capabilities of a potentiometer. So when I start with encoder, I'm going to talk about the functionality of the encoder, and then we'll go through a sample program. So this picture shows you the potentiometer and the rotary encoder. And physically, they are somehow similar, but the rotary encoder is a digital, the potentiometer is an analog device. So rotary encoder and potentiometers are both used to measure and control rotational movement. So either you rotate the potentiometer or you rotate an encoder, that's going to send a signal to the microcontroller, and then you have to take some action. So let's look at the differences. So the rotary encoder is digital and the potentiometer is an analog device. Now the output for the rotary encoder is a pulses or digital code. That means that I can hook up my rotary encoder to any port in the microcontroller. On the other hand, the potentiometer output is variable resistance or voltage. What that means is that I have to hook up the potentiometer to a analog to digital conversion port. So a port that has capability to convert analog to digital, not to any port. Precision, the rotary encoder is high, the potentiometer is moderate. Lifespan, the rotary encoder is long, potentiometer short. Environment, harsh environment rotary encoder, limited by the ceiling for the potentiometer. Applications, rotary encoder, we have robotics, motors, CNC, UIs. On the other hand, potentiometers is volume control, light dimming. When it comes to cost, rotary encoder is higher than the potentiometers. So anyhow, at this point, I'm going to switch to talk about only rotary encoder and how to program those. So rotary encoder, we have three types: the optical encoder, magnetic encoder, and then quadrature encoder. The optical encoder uses light and photodetector, a rotating disc with transparent and opaque segment interrupt the light, creating the pulses. Now for the magnetic encoder, uses magnetic field generated by a rotating magnet detected by Hall effect or magnetoresistive sensor. And finally, we have the quadrature encoder. typical provides two output signals, A and B, in quadrature. That means 90 degrees out of phase. This enables detection of direction and position. And this is what we're going to be writing our program, and this is the encoder we're going to be using. The simplest. Let's see how it works. So for clockwise. So this is what this thing looks like. This is, we're going to rotate this circle, and now the gray area are hooked up to ground, and the white areas are hooked up to 5 volts. So let's see what happens when we rotate. Now we have output A and output B that are fixed. So let's rotate clockwise. So when we rotate clockwise, we see that output A reaches the area with 5 volts, while output B is still on the ground. So the output at that point is going to be A1, B0. So let's continue rotating. Now at this point, as we continue to rotate, we see that output A and output B are both on the 5 volts, so that's a 1-1. And then finally, with the last rotation, we see that output A got into the area which is ground, and output B is still on the 5 volts, so it's 0-1. So now let's see what happens when we rotate counterclockwise. So we start as before, and then we rotate counterclockwise, and we see the output A is 0 and output B is now 1. It's opposite as before. Next we rotate one more time, and they are both 5 volts. And then let's rotate one more, and then we see that it's A is 1 and B is 0. So what I want to show you here is that when you rotate in one direction, you get a set of outputs. While you rotate the other direction, you get a different set of output. So you can use some logic to figure out what's the sense of the rotation. So let's talk about let's go to the sample program, because that's where everything is going to come together. So this is the rotary encoder. So it has a rotary where you can move it, you can rotate it, and you have a push button also. Here you have a pin A, pin B. This is the push button. And then we're also going to have a laptop hooked up to the controller and a LED. So the push button is going to be hooked up to pin D2, which is interrupt 0. And pin A is going to be hooked up to port PD3, which is hooked up to interrupt 1. And then pin 6, D6, is going to be hooked up to port B, so we can read the output. And then we'll have our transmit receive ports hooked up to the laptop. So let's see a program statement. Use interrupt INT0 to monitor the rotation encoder switch. Use interrupt INT1 to monitor rotation encoder output A. Output pin A, push button. Use pin 6 as an input connected to rotary encoder in pin B, so we can read the output from the encoder, pin B. If rotation encoder is rotated clockwise, increment a counter and display results in the laptop. Next, if rotary encoder is rotated counterclockwise, decrement the counter and display the result in the laptop. So clockwise, increment counter, display in the laptop. it is clockwise, increment, counterclockwise, decrement, and display it. If the rotary encoder push button is pressed, then set the counter to 0 and display the result in the laptop via UART interface. So no matter where you are in the account, if you push the button, you set up to 0. Bouncer will handle by introducing delay, 300 milliseconds in this case. Okay, so let's see how we're going to program this stuff. So we have input A and input B to the microcontroller. Input A is hooked up to the interrupt. So as soon as the input A goes high, that means the interrupt triggers, and then if we look at the input B and it's 0, we're going to decide that is clockwise. As you can see, every time the interrupt is triggered, the signal is high, then if we read the B input, it's going to be 0. And that's because there is a 90-degree difference in phase between these two signals, and that's always going to be true. So if it's going clockwise, the interrupt, we get an interrupt, we read B is 0, we know we're going clockwise. So let's read this. Rotary encoder output clockwise rotation. If an interrupt is triggered on the rising edge of the output A and output B is low, then we know that the rotation is clockwise. Now let's look at the other case. The interrupt gets triggered on A, and then we look at input B and it's high. If that happens, we know that the switch we know that the rotary encoder is being rotated counterclockwise. And this is always going to be true when it goes counterclockwise. And that's because of the shift, the way that's set up in the 90-degree offset. So let's read at the statement that puts all together. If an interrupt is triggered on the rising edge and the output A and output B is high, then we know the rotation is clockwise. So the interrupt gets triggered, input A is 0, is 1, we know that we're going counterclockwise. If the interrupt is triggered and input B is 0, then we know it's going clockwise. So let's see how the logic is going to go. So set up interrupt to trigger on input A rising edge. So did the interrupt trigger? Yes. Is input B 0? Then we increment the counter. If it's not 0, then we decrement the counter. So let's look at the code that will handle this. So first I'm going to give you a global view of the program, and then I'll get into the details. So we have a routine that's going to initialize all the ports. Now this program is going to be using interrupts. So we have a routine to enable and disable interrupts. We have a routine to set up, initialize all the interrupts. Next, let's go to the main program. The main program is going to initialize whatever needs to be initialized, and then it's going to send a message to the UART and turn on and off an LED, which is basically a heartbeat. Let the user know that, yeah, you applied power and we are up and running. Finally, we have two interrupt service routines. One is going to be responsible for incrementing and decrementing the counter based on the rotation. And finally, we're going to have one interrupt service which is going to monitor the switch. If the switch gets pushed, then it's going to set the counter to 0. So let's get into the details. So in need ports, what we have is we're setting up the pin B1 to output. That's the one that's going to turn on and off the LED. And then it's going to set the pin D6 to input. Also, in addition to the pin D6 being input, we also will have the pin D3 and pin D2 to inputs. However, I have not incorporated those into the need ports because by default they are inputs. All the pins by default are inputs. So I wanted to purposely leaving that out so I would remember to mention it. So here the pin D6 I showed and set it up as input, but if I didn't do it I would have been fine because the pins are set up to inputs by default. I like better to set them up to inputs so you visually see what things are doing. And finally I put a pull-up resistor for all the input pins. That would be pin D2, D3, and D6. We don't want to have any floating inputs. Okay, so next let's see the enable and disable interrupts. These are just the line of code which enable globals or disable global interrupts. So now let's look at the routine that it needs the external interrupts. So we have interrupts associated with INT1, which would be pin D3, and we have pin A associated with that. Then we're enabling the interrupt associated with pin INT0, which is pin D2, which we're going to hook it up to the push button. And finally, what we do on this routine is we enable those two pins to start working as interrupts, INT0 and INT1. If a signal comes in, then the interrupt will be triggered. Now let's head to the main. So what do we do on main program? So we need ports, we need external interrupts, and we also need the UART because we're going to be displaying the counter numbers in the laptop. We can see it right here. Then next we have the heartbeat. We turn on and off the light for 50 milliseconds. And we also have a hello message for the laptop. So now let's look at the two interrupt service routine. The INT1 vect, which is this one here, is going to be associated to pin A. So if we are in this interrupt service routine, we know that we got an input from pin A and in port PD3. So the first thing we do is using a mask, we extract the bit that triggered the interrupt, and we put it into the parameter state. Now, if a state is 0, then we know that the counter has moved clockwise. So what we do is we first ask, hey, is the counter already in its max value? And if the answer is no, then we increment the counter. Now, if the value is yes, then we don't do anything because we already got to the max. So no matter how much you rotate that switch, nothing is going to happen. So that's if the state is not 0. Because don't forget we're using pull-up resistor. So if we did not use a pull-up resistor, then we would do this logic if this would be 0. But we're using pull-up resistor, so it's the opposite. So if it's not 0, we move clockwise or do nothing if we already got to the max value. Now, if the value is 0, then what we do is we ask, hey, are we at the minimum value? If the answer is no, then we decrement the counter. Otherwise, we increment. Otherwise, we do nothing. So let me say it again. If the rotation value is already at its minimum, we do nothing. If it's not at its minimum, then we decrement the value. After we've incremented or decremented the value of the counter, then we turn on and off an LED. That's like a heartbeat, saying, hey, we're doing work here. And then we display the value of the counter on the laptop. So how we do that is we send the counter value, and then we put the word in rotation. Finally, we have a delay of 300 milliseconds, and that's just to take care of some of the bouncing. And then finally we enable the interrupts, and we're done with tasks associated with the counter. That's the PD3 INT1. Now, if the user pushes the button, then it's going to trigger INT0 interrupt here. So what we do here is basically we disable the interrupts so we don't get interrupted while we're in the interrupt. Next, we've turned on and off and the LED just to let the user know we are doing some activity. And now the rotation counter, we set it to rotation to counter minimum, which is 0. So the rotation counter gets set to 0, and then the output, which should be 0, gets displayed in the laptop. So we set 0 and then in push button, so the user knows that maybe if it has a value of 20 here, then the next one is going to be 0, and we state is due to in push button state. Next, we wait about 300 milliseconds, and then we enable interrupts. So let's look at the output. So you can see here we have our hello world. Then we go, I'm rotating the switch clockwise, 1, 2, 3, 4. Then I'm going backwards, 3, 4, going forward again, 5, 6, 7, 8, 9, 10. And then I keep rotating after I get to the maximum, but then it doesn't change, stays in 10. Then I start decrementing. I have 9, 8, 7, 6, 5. And then I push the button. It says in push button, it sets it to 0. Then I increment to 1, 2, 3, and then I push the button to, and then it goes to 0, and then I try to decrement, and it says no, you are already in 0 rotation. And then I go 1, 2, 3, 4, and then 2, 1. So anyhow, you can see how this works. And one of the things that I forgot to note here, so you can set up what's your counter maximum. I decided to use 10 and counter minimum 0. But I mean, you could put whatever number should be here, and as you would increment it to 100, and the minimum also. It's something that you set up. So that concludes the descriptions of this program. Okay, so we got to the summary. Today I talked about potentiometer. I also address encoder, and then as it relates to the encoder, I provided some definitions and also a sample program related to encoder. So anyhow, thank you very much for taking the time to spend it with me, and hopefully I'll have another presentation pretty soon. Thank you very much.